Have you ever wondered what makes some solutions conduct electricity while others do not? Well, the answer lies in the fascinating world of chemistry, more specifically in the realm of electrolytes and non-electrolytes. These are terms that may sound complex at first, but we'll break them down into bite-sized, digestible pieces for you. So, what are electrolytes and non-electrolytes? Let's start with electrolytes. They are substances that produce an electrically conducting solution when dissolved in a polar solvent, such as water. The dissolved electrolyte separates into cations and anions which disperse uniformly through the solvent. Think about when you dissolve table salt or sodium chloride in water. The sodium and chloride ions separate and move freely in the water, allowing the solution to conduct electricity. On the other hand, non-electrolytes are substances that don't dissociate into ions when dissolved in water. As a result, they don't conduct electricity. A common example is sugar. When you dissolve sugar in water, it breaks down into molecules, not ions, so the solution doesn't conduct electricity. You might be wondering, why does this matter? Well, these concepts are not just confined to the chemistry lab, they're crucial to our everyday lives. For instance, the human body relies on electrolytes for many essential functions. These include maintaining hydration, balancing blood pH, and supporting nerve and muscle function. Non-electrolytes, like glucose, provide energy to our cells, but it's not just about biology. In the world of technology, electrolytes are used in batteries to conduct electricity. Non-electrolytes, on the other hand, find use in various industries, including food and pharmaceuticals, where they perform functions ranging from sweetening your morning cup of tea to acting as an active ingredient in your medicine. So the next time someone asks you about electrolytes and non-electrolytes, you'll be able to explain with confidence. Understanding this difference is the first step to unravel the exciting world of electrolytes and non-electrolytes. Now that we know what electrolytes and non-electrolytes are, it's time to dive deeper into the world of conductance. Let's start with equivalent conductance. What is it? Well, equivalent conductance is simply the conductance of an electrolyte divided by the amount of the electrolyte. It's a way of measuring how effectively a substance conducts electricity, taking into account the amount of substance present. Now imagine you're running a marathon. The more energy you have, the faster you can run, right? In a similar vein, the greater the equivalent conductance of an electrolyte, the better it conducts electricity. It's like saying the more electrolyte you have, the better the conductivity. But what about specific conductance? Well, it's another way of looking at how well a substance conducts electricity. But instead of considering the amount of substance, it considers the length and area of the path the electricity has to take. So if we stick with our marathon analogy, specific conductance is like considering the distance and terrain of the marathon course. The longer the course and the rougher the terrain, the harder it is to run fast. Similarly, the longer the path the electricity has to travel, and the narrower the path, the lower the specific conductance. So, equivalent conductance is about the runner, and specific conductance is about the course. Both these measures are crucial in understanding and predicting the behavior of electrolytes. They help us quantify not just if a substance will conduct electricity, but how well it will do so under different conditions. So, to sum it up, equivalent conductance tells us about the capability of an electrolyte to conduct electricity, considering the amount of electrolyte, while specific conductance considers the length and area of the path the electricity has to travel. Both are equally important and serve as invaluable tools in the field of chemistry. The story of conductance doesn't end here, as we're about to see next. Have you ever heard of Kohlrausch's law or conductometric titrations? Let's delve into these fascinating concepts. Kohlrausch's law is a cornerstone in our understanding of electrolytes. It's named after Friedrich Wilhelm Georg Kohlrausch, a German physicist who made significant contributions to the field of electrochemistry. Here's what his law states. The molar conductivity of an electrolyte at infinite dilution can be expressed as the sum of the individual contributions of its constituent ions. In simpler terms, it means the more you dilute an electrolyte, the more you can predict its conductivity based on the ions it contains. This law provides valuable insights into the behavior of electrolytes, aiding in the development of countless applications from batteries to medical treatments. Now let's turn our attention to conductometric titrations. This is a titration method that measures the electrical conductivity of the reaction mixture to monitor its progress. Why is this important, you ask? Well, it's because conductivity can reveal a lot about the presence and concentration of ions in a solution. In conductometric titrations, we gradually add a solution of known concentration to a solution of unknown concentration. As the reaction proceeds, the conductivity changes, creating a unique profile that can be used to determine the endpoint of the titration. This method is especially useful when the reaction doesn't involve a significant color change or when the solution is already colored, making it difficult to use visual cues for the endpoint. So, to sum it up, these two concepts, Kohlrausch's law and conductometric titrations, give us powerful methods to study electrolytes. They help us understand the nature of ionic solutions, and they allow us to measure concentrations with precision. Kohlrausch's law and conductometric titrations are key tools in understanding electrolytes, but there's still more to explore. Stay tuned as we journey further into the captivating world of electrolytes. Are you ready to learn about the fascinating colligative properties of electrolytes? Let's dive right in. Colligative properties are those properties of solutions that depend on the ratio of the number of solute particles to the number of solvent molecules in a solution and not on the nature of the chemical species present. These include freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. Now, how do electrolytes come into play? Well, electrolytes, when dissolved in a solvent, separate into ions. This increases the total number of solute particles, thereby magnifying the colligative effects. Non-electrolytes, on the other hand, do not dissociate into ions and hence do not exhibit the same behavior. Let's take freezing point depression as an example. Imagine you're making homemade ice cream. The reason we add salt to the ice is to lower its freezing point, which makes the ice colder than it would be otherwise. Here, salt is acting as an electrolyte, and the more salt you add, the lower the freezing point will be. The same principle applies to the de-icing of roads in winter. Boiling point elevation is another fascinating colligative property. Think of it as the opposite of freezing point depression. Adding an electrolyte, like salt, to water raises its boiling point. This is the reason why food cooks faster in salt water. These are just two examples, but the colligative properties of electrolytes extend into many aspects of our daily lives. From the functioning of our cells to the production of electricity in batteries, electrolytes and their colligative properties are crucial. In essence, colligative properties of electrolytes are a fascinating topic that combines the realms of chemistry and everyday life. They illustrate how the microscopic behavior of atoms and ions can have macroscopic effects that we can observe and utilize in our daily life. As we've seen, the colligative properties of electrolytes are intriguing, and they are just a part of the larger picture. We've covered a lot of ground today, from the basics of electrolytes and non-electrolytes to Kohlrausch's law and colligative properties. Let's take a moment to reflect on what we've learned. We kicked off our journey by distinguishing between electrolytes and non-electrolytes. Remember, electrolytes are substances that, when dissolved in water, produce ions and conduct electricity. On the other hand, non-electrolytes don't break down into ions and therefore can't conduct electricity. Next, we explored the concepts of equivalent and specific conductance. Equivalent conductance is the conductance of an electrolyte divided by the amount of the electrolyte, measured in equivalence in the solution. Specific conductance, meanwhile, is simply the conductance of a solution between two electrodes 1 centimeter apart and 1 square centimeter in area. These concepts are crucial in understanding how electrolytes behave in solution. Then, we dived into Kohlrausch's law and conductometric titrations. Kohlrausch's law states that the limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation. Conductometric titrations, on the other hand, are a type of titration in which the electrolytic conductivity of the reaction mixture is continuously monitored as one reactant is added. Lastly, we delved into the colligative properties of electrolytes. These are properties that depend on the ratio of the number of solute particles to the number of solvent molecules in a solution, and not on the nature of the chemical species present. These concepts are not just isolated facts. They are fundamental building blocks in chemistry. They help us understand everything from the behavior of cells in our bodies to the operation of batteries in our devices. This is just the tip of the iceberg when it comes to electrolytes and non-electrolytes. There is so much more to uncover and understand. So stay curious, keep exploring, and always ask questions. And remember, subscribe for more because you won't find me later.